Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon. This is going to be part 2 of our frequency response technique. Some of the slides I may show again. Some I'll just skip quickly. This one we have seen for first order system. See that the AR and phase lag depends on frequency. And this is related to the first order system with sinusoidal input. Second order system also the AR depends on the omega, and the phase lag depends on omega, the frequency, and the relation with the before, the amplitude ratio is the output over the input. So the output amplitude ratio divided by input. Input is A, the output is A over this one, and then when we divide it becomes D. So this is amplitude ratio when we plot for the this AR plot, and the phase angle plot is given in this form. For that systems in series, the total AR and total phase lag is just the addition of each individual AR and in each individual. So the total overall AR is just the multiplication of all the AR for each individual system, and the overall phase lag is the addition of the phase lag of each individual system. The controllers, like you seen before, is independent, zero independent of the phase lag for the AR KC controller. For the PI controller, dependent on the omega, and of course also dependent on the tau I. Same with PD, AR dependent omega, phase lag dependent on the omega and tau D. PID the same thing, phase lag dependent on omega and the tau I and tau D. The body diagram, convenient plot where we plot log AR versus log omega, phase lag versus log omega. This is a semi-log graph. This is the log graph. So we have the two curve and we have the three low frequency, high frequency. Corner frequency is the change between the low frequency to high frequency, then changes. And we see here we are plotting. We can plot log AR versus log omega, or we can plot log AR versus omega itself. Depending. If we have one time constant, we can plot against omega tau. If we have many time constant, many system, then we have to plot against log omega only. Plot against log omega, omega tau, then it's at omega tau equals to 1 is where the corner frequency is. Omega tau equals to 1, so the corner frequency is at 1 over tau. This is we plot omega tau, it is at 1. We plot against omega, it is at the corner frequency as at value of 1 over tau. This is the same phase angle plot. Again, I said when we plot against omega tau at corner frequency, it is at omega tau 1, which means that it's at omega equals to 1 over tau, time constant system. So the corner frequency place where the low frequency asymptote covers the high frequency asymptote, the change of gradient, yeah, from 0 to -1. Second order system, you can plot omega t, you can plot against log omega tau, and you can see that omega tau is 1 is the corner frequency, and of course depends on zeta, so we have different curves for zeta, but the asymptote line is -2 because that is for second order system. In system in series, just an additional multiply or add on, and we take the log, it's addition of the different individual amplitude ratio and addition of the different phase lag. And we can see this in the example here from the book. So you get two systems, and the overall is gradient changing from -1 to -2. So this is fixed diagram and so on. We can see the different body class. Okay, for this example, you see in the textbook, we are trying to plot the overall body plot for this open loop transfer function. Okay, we just need to talk about open loop transfer function for our purpose here in the next chapter. So basically we have to open loop is just this times this times this. So this is the open loop transfer function. So we're going to have to plot them individually and then combine them. Okay, so let's look at this first part. This first part is the P T controller. We have a KC10 and tau d half. So this is the transfer function here. So the plot is basically low asymptotic here, and the high asymptotic is +1 gradient, because this is the transfer function +1 gradient. Okay, since we are dividing the overall by 10, which is the value of the KC, so we can start with 1. If not, we have to start from 10, the value at 10. So since we are dividing, can we do it? So we can start at 1, and we have to plot against omega because we have so many taus here. Can plot omega tau, we have to plot against omega. So this is the first one for the transfer function, PD transfer function. Then we see about the second plot. Okay, let's look at how we plot for this one. What is the AR for exponential E s over 10? It's just 1. Just 1, so we don't have to worry about the AR value. What is the, then we look at this transfer function 1 over S1 plus squared. So the asymptotic plot, we're just looking at asymptotic plot. The phase angle we just add on. We can take the overall phase angle by asymptotic plot. For the S1 squared, so it's a matter of doubling twice this S plus 1 squared. So if you have just 1 over S plus 1 is it cross at the tau is 1, so the corner frequency is 1, so it has a gradient -1. Add on another 1 over S plus 1, another -1, so -1 and -1 we get -2. So this is the plot 1 over S1 plus squared, gradient of -2, corner frequency here. Right. So this is a first order system. What is the corner frequency? Corner frequency is at 1 over tau. What is tau? 1 over 10. So it means at corner frequency 1 over tau, which is at 10. So at the value of 10, yeah, that's where the corner frequency for the low asymptote and high asymptote for this transfer function. So this is going to be the asymptotic plot, which is at -1. Okay, so these are the individual plots for this one, for 1 over S1 plus squared, this dotted line, you can see the dotted line. Now we're going to get what is the overall. Okay, now we're going to get the overall. The overall is just adding on the asymptotic plots, which is very simple, just method of adding on the gradient. So we can see the overall is at this point is the same, comes here. At this point, the gradient is -1. The gradient is -1 and -1, -2 is greater than -2 here. But at this point of the corner frequency for this transfer function is +1. So it's -1, -2, +1. So it's another back to gradient -1 here. At this point, from here to here. At this point at 10, it becomes another -1. So you got -2, +1 becomes -1, and then back to another -2 here, because this one becomes -1. So this overall is just this one here, here, and here. So that's how it's easy when we plot using asymptotic plot. It's just a matter of getting the corner frequencies and adding on the gradient at those points, different gradients at different points. So this is the overall curve with the derivative action. Without derivative action means this part, we don't have this part that goes straight down. But if you have with derivative action, then you get a different slope change here, and it will go to -2. Without, if you don't have this, and it is -2, but at this point you add another one to become -2 here, and it goes to -3 here. We can't see here, it goes to -3 here, because additional of -2 and another one -1. But because you have a +1, change back to -2. So this is the overall asymptotic plot that you can easily do in fact by hand, but you can also use by MATLAB to plot this on the phase angle. It's just a matter of additional of all the phase values, add on and draw the phase angle. And right, again, as I said before, you can plot like AR or AR over 10, and that's what you get the final plot against omega. And to summarize this in summary of the different amplitude ratio values you get for the system, phase lag, first order lead, phase lag, integral, derivative, second order transportation lag, what are the corner frequencies and the slopes involved. What we have, this is just to summarize. And for first order, we said when omega tends to infinity, it goes to minus. So this is the maximum phase lag you get first order system. For first order lead, maximum is plus 90. This is phase lead, giving lead, because this is a transfer function at the numerator part. Okay, and for second order system, what is the maximum? Maximum is minus 180 degrees. For this one is fixed, minus 90 plus 90 constant, transportation lag, it goes on and on and on. So these issues of maximum phase lag give us some idea of stability. We'll see later. You got some connection with stability. Minus 180 degrees basically is the point of instability. So we can use this to design our stable systems where the phase lag cuts at minus 180 for this, and especially for this. And this one, it doesn't, the phase lag keeps on going and going as long as omega changes. And this is the problem of stability with transportation lag, as we've studied before, and we will see in our next class how transportation lag will definitely make the system unstable. Okay, thank you very much for your time.